Good morning, everybody. We're going to take a look at conservation of mechanical energy today. This is a review of something we did first semester that we're going to apply to pendulums and mass spring systems. So we're now going to be applying energy to simple harmonic motion. This should not be too difficult. It's something that you guys are pretty familiar with, but with that said, we're just going to do a quick review, and then you guys can get to your work today. So, conservation of mechanical energy is what we're looking at. Mechanical energy is defined as kinetic energy plus potential energy. So this guy right here, very, very important. Mechanical energy is just, it's kind of like the total energy of the object, but it's not really the total because there are some other energies such as mass energy that we're not concerned about. But yeah, it's the kinetic energy of motion plus the potential energy, which is considered energy of position. So typically, potential energy is one of two kinds. It's either gravitational potential energy, which we see right there, or it could be elastic potential energy, which we see right there. So if we're talking about a pendulum, you're going to have PEG, and if you're talking about a mass spring system, then you're going to have 1/2 kx squared, where k is the spring constant, and x is how much you displace that spring, how much you stretch it or compress it. With that said, kinetic energy is always 1/2 mv squared, which is, again, just, the energy an object has for motion. As a friendly reminder, the units for energy are joules, which is abbreviated capital J. So typically we just write a capital J after our units. And if you're curious, a joule happens to be the same thing as a kilogram times a meter squared per second squared. So that's the full definition of a joule. All right, now what we need to remember is that the mechanical energy of any closed system is always conserved. So what do we mean when we say a closed system, and what do we mean when we say conserved? So hopefully you guys remember what conserved means, but just to be clear, first of all, a closed system very specifically means no friction, right? And no air resistance. And it means basically no other forces at all, okay? So no forces. So no other outside forces, I should say. So no outside forces. So for example, you could have a pendulum, and that could be a closed system all by itself, but there's a force of gravity acting on the pendulum, but that's not an outside force, that's a force that's part of the system. So in any case, when we say closed system, we just mean that there's no friction, no air resistance, there's no energy leaking out, and nobody's messing with it, it's just left alone, right? Now what does it mean to be conserved? Well, if we say that the total mechanical energy is conserved, then what we mean by that is the total mechanical energy, that number, the value for that energy will stay the same. It'll stay constant, right? So just like momentum is conserved, the total momentum remains constant. Energy is conserved, the total energy remains constant. So that should sound familiar to you. So when we say conserved, we mean the total amount stays constant. Cool. So, with that in mind, we can go ahead and get started on, writing some equations here and understanding how we practically deal with this. So, if mechanical energy is kinetic plus potential, and we're saying the total mechanical energy stays constant, then what we mean is the mechanical energy that we have in the beginning is equal to the mechanical energy that we have at the end. And this means that we could expand upon this a bit. We could say that the total kinetic plus potential energy that we have in the beginning, whatever that is going to be equal to the kinetic and the potential energy that we have at the end. So we add those two together. So I, of course, initial, F, of course, final. And so the total will not change, the total will stay the same. So this is a pretty important equation. I'm just going to box that real quick. And then, of course, we know that kinetic energy can be written as 1/2 mv squared. So we can expand upon this further. And that 2 is ugly. There we go. And that velocity would be initial because the velocity of the object is what could change. So it could be moving at one speed in the beginning, it's going to be moving some other speed at the end. And then the potential energy, right here, mgh. What of these variables, mg or h, is going to change? It's going to be the height, right? So that's going to be the initial height. So the pendulum, for example, is going to start maybe high up, and then it's released. So at its lowest point, it's lost its height, and then later on, it gains its height back. So the height varies. And then kinetic energy, 1/2 mv squared, but the velocity is final now. That's an ugly F there. I'll fix that. That's a little better. And then we have mgHf, right? Now for a spring, keep in mind, we might not have a bunch of potential energy. Instead, we might not have a bunch of gravitational potential. For a spring, we'll probably have, 1/2 kx squared exclusively. So this is really more geared towards pendulums right now, but that's kind of more what your assignment is today, so you don't have to worry about mass spring systems and their energy for now. But you could imagine very easily replacing this mgh here and here with just 1/2 kx squared, where k would be constant and then x would have an initial and a final attached to it. So that's kind of like what that would look like. In any case, we're going to plug in some quick numbers here to just reinforce the idea of what it means to be conserved. And so what we mean when we say it's conserved is that, you might start with a certain amount of kinetic and potential energy, right? So let's look at a pendulum, okay? And we're going to say the pendulum is going to be right here. It's going to start at its maximum displacement, okay? So the equilibrium point, actually, we'll make this, can I do a dotted line? Well, that's kind of ugly, but we'll try. So it's going to start with some initial angular displacement here, which is its amplitude, okay? So it starts with some displacement. That's the maximum displacement from equilibrium. There's its amplitude, right? So the pendulum here, it's going to have a certain height associated with it, right? And, well, that's too tall, isn't it? Let's just lower that a bit. Maybe this is its height, right? And that height h is right there. But if you're holding the pendulum, you pull it back and you're holding it, then in the beginning, the pendulum only has potential energy. It doesn't have any kinetic energy, right? So then in the equation, we're going to take this equation here. We can bring that down there, right? If we bring this equation down there, then what we have is 0 kinetic energy, and we'll have whatever potential energy it might have. Now, I could plug in mgh, but for now I'm just going to pretend like, the potential energy happens to be 100 joules. It doesn't matter what the units are. So we'll just say the potential energy is 100 in the beginning and the kinetic energy is 0 because we pulled it back and we're about to release it, right? So then what's going to happen later? Well, there's a few laters that we could consider. The first later we could consider is, when the pendulum is all the way down here at the bottom, right? So now it has swung. Now remember, the swinging motion is going to be back and forth like I'm drawing here, right? So that's what we're talking about when we see this pendulum swinging back and forth. But we're just going to let it go to here, and then we're going to stop it. We're going to freeze time, and we're going to look at the energy. Okay, so here the pendulum is going to be actually moving right here pretty fast, okay? Because in fact it'll be moving at its maximum speed there, and we know that because it can't get any lower, right? So if it can't get any lower, what can we conclude about the potential energy here? Well, if it can't get any lower, then we know that the potential energy would be 0 because the height would be 0. In other words, even though this might be off the ground, we can define this line right here, we can define this line as our 0 height if we wanted to. And so we can say, okay, therefore the pendulum has no potential energy in the middle there. So that just means that whatever energy we had here, well, the left-hand side and the right-hand side of this equation have to be equal, so that means our kinetic energy must be 100 joules. And that's very important. Now, if I know that, of course, then really what I can do is I can then calculate the velocity of my pendulum, because if I, of course, know the mass of my pendulum, then I can find the velocity by solving for v, okay? So that's the general approach we'll take, is, just sort of look at what's happening with the system and try to write an understanding of the energy, answer a question by solving for the velocity or the height or something like that. So just to give another quick example, what if we look at the pendulum at a slightly later point in time, okay? So maybe the pendulum now here is not at maximum displacement, it's just further to the right, okay? So it's swung a little bit more. So now we know that in the beginning it still had this situation, right? We still had 0 kinetic energy at the beginning, and we still had 100 joules of potential energy at the beginning, because after all, we're talking about right over here, okay? And that hasn't changed. So we have that situation still on the left. That can still be our initial. But then we're going to examine this part right here, and if we examine that position, then we know that the pendulum is going to have both kinetic and potential there, right? So, for example, I might actually be told that the pendulum is a certain distance high right here, right? So the pendulum has a height. And if I'm told that height, then I can calculate the potential energy of the pendulum. Well, let's suppose I'm given that information and I say, oh, look, let me plug in MGH, and I got 30. I got 30 joules for my potential energy at this point right here. Well, then I automatically know how much kinetic energy the system has, right? So instantly, if you look at the numbers, you can tell that there's 70 joules of kinetic energy. But how do we know that's 70? Well, because what we're really doing here is we're pretending, or we're plugging in kinetic energy to this equation, and we're just doing mental math. But if the math is, too difficult to do in your head, you just write this equation out, and then you simplify it, and you just solve it, right? So you just do one of these, 100 minus 30 from both sides equals kinetic energy, and then you have your kinetic energy. And once again, once you know this number is 70, then you can go ahead and find your velocity by plugging in your mass and solving for v. So that's pretty much it. Your assignment today isn't going to be super difficult. It's 2 problems. Of course, they have parts A through E, but it should be pretty straightforward. I think you guys will probably not struggle a whole lot. But I figured I'd make this video and upload it. So with that said, I'm not going to assign any break homework. So spring break is homework free for you guys. I wish you a very safe and very restful spring break. And I look forward to working with you guys online for the foreseeable future when we return. So take care, guys.